So today we're going to look at arterial blood gas interpretation, the approach to how you should do it in the FCA Part 1 exam. Now I know when we think about this kind of question in the exam, we feel like this little girl freaked out, but hopefully after following the 5 steps that we're going to go through in this video, you're going to feel more like the girl on the right. So what do we need to do? We need to evaluate the PaO2. Then we need to evaluate the pH. Next, we need to evaluate the pCO2. Fourthly, we need to evaluate the metabolic component. And lastly, we're going to look for any compensation and how adequate it is. So nothing new, we do this every day in theatre, we just need to put it into a formal exam answer. So let's look at these one by one. First of all, evaluating the PaO2 and the AA gradient, we basically want to see if there's any hypoxia and or hypoxemia. So first of all, hypoxemia, that's the easy one. Is there enough oxygen in the blood? And the cutoff that we use here is a PaO2 of 60 millimeters mercury or 8 kPa. Now just a little trick that we should know. To convert between millimeters mercury and kPa, you just divide or multiply by 7.5. So let's look at a blood gas example. This is the whole blood gas, but we're going to just zoom in on the little bit that we want. And if we look at this, the PO2 is 167. So clearly there is no hypoxemia here, but we now need to decide if there is hypoxia. Now the difference between hypoxia and hypoxemia. Hypoxemia, as we said, is basically just whether there's enough oxygen in the blood. But hypoxia is whether that oxygen that we're giving is getting to the tissues. And here we need to look at the gradient between the amount of oxygen in the alveolus and the amount of oxygen in the artery. Okay, so first we need to work out the alveolar oxygen content, and we do that by using the Alveolar Gas Equation. And that is, and you're going to see it now, it's P big A O2, which is equal to the fraction of inspired oxygen times the atmospheric pressure minus the saturated vapor pressure, and subtracted from that the PaCO2 divided by the respiratory quotient. Now don't worry about all of these, we're going to go into it bit by bit that you understand it. So in this alveolar gas equation, there are basically 3 parts that we are looking at. The first one is the content of oxygen in the atmosphere. And for that, we need to take the fractional inspired part of oxygen and times it by the atmospheric pressure. Now, the atmospheric pressure will always be at sea level. They will state that in your test, and you just need to remember that that is 760 millimeters mercury. So if we work that out, we get 160 millimeters mercury. That's the partial pressure of oxygen in the atmosphere. Right. The next thing, we want to work out the content of oxygen in the trachea. Now remember that as you inhale air through the nose, you're actually moisturizing or humidifying that air. So it's almost like we need to make space for some water vapor. So from the atmospheric pressure, we're going to subtract the saturated vapor pressure of water, which you just need to remember is 47 millimeters mercury. So if we work this out, we see that normally when we breathe in room air, there should be 150 millimeters mercury of oxygen. That's a partial pressure of oxygen in the trachea. But now we're moving down into the alveoli. And remember, in the alveoli, there's not only oxygen and air, but we also need to make space for CO2. So from our initial calculation, we are going to subtract the PaCO2. Now the PaCO2 is divided by something there, something called R, and that R is called the respiratory quotient. And we'll go into that in a little bit more detail. Okay, but if we work it all out, we see that the content of oxygen or the partial pressure of oxygen in the alveoli works out to 100 millimeters mercury. Okay. So just to understand this equation a bit better, let's look at a couple of physics concepts. The one is that of the saturated vapor pressure of water. Now it's important to remember that the saturated vapor pressure is not dependent on the atmospheric pressure. Whether you are at sea level or whether you are up at Everest, the saturated vapor pressure is the same because it is dependent on a temperature. So what is the saturated vapor pressure of water or of any other substance? Now I'm going to draw you two containers just now, and we know when we have liquid in a container, there will be some particles that gain energy and they are going to escape into the atmosphere. They evaporate. Now if we change this to a closed container, some particles will still escape, but they obviously now can't evaporate completely. They go into vapor form, and those particles exert a pressure on the container, and that is the vapor pressure. As you increase the temperature inside of the liquid inside the container, more particles are going to escape into vapor form. But of course, you will reach an equilibrium where some particles will lose energy and go back into the liquid form. And when those two states have reached equilibrium, we call that the pressure that is exerted by the vapor above the liquid, we call the saturated vapor pressure. So you can see that it is purely dependent on the temperature of the liquid and the vapor, nothing to do with the atmospheric pressure at all. Okay. And there's actually a graph that one can look at, and we'll bring that up on the screen just now. And that graph shows us that as the temperature goes up, so the saturated vapor pressure goes up as well. So at room temperature, the saturated vapor pressure of water is 20 millimeters mercury, and at 37 degrees, which is body temperature, the SVP for water is 47 millimeters mercury. So you just have to remember 47. The next concept that we need to understand in this equation, if you remember when we had the equation, the PaCO2 was divided by a constant called R, and that R is the respiratory quotient. It's also called the respiratory exchange ratio. And basically what it is, it's a dimensionless number or a unitless number, and it is purely the ratio of the CO2 that is eliminated for the oxygen that is consumed. And what is interesting about this is that it depends on what you eat, because different foods have different numbers of carbon molecules and takes a different amount of oxygen to break down. So if you eat mostly protein in your diet, or only protein in your diet, then your respiratory quotient is 0.8. Whereas if you eat a lot of carbs, then your respiratory quotient is going to be 1, which I think is the reason why the concept of carbo loading came in terms of exercise, because it makes your respiratory quotient better. If you eat a diet that consists of fats only, then you're going to look at a respiratory quotient of 0.7. For the most part, in the exam, they will not tell you anything, and then you can assume that the patient eats a mixed diet. And for a mixed diet, the respiratory quotient that we use is 0.8. So basically all that you need to remember is in this equation, your atmospheric pressure is 760, your saturated vapor pressure is 47, and your respiratory quotient is 0.8. And then your FiO2 and your PaCO2, they will give you. Okay. So basically what we've done now with this equation is we've looked at the oxygen cascade. And if you look in Cross and Plunkett, page 132, you will find this page there. So please make sure to have a look at that. Okay, so keeping all of that in mind, let's now look at our example blood gas again, and let's work out if there is hypoxemia and hypoxia. So to the question, is there hypoxemia? We can see that the PO2 is 167 millimeters mercury, so that looks fine. So no, the PaO2 is more than 60 millimeters mercury. There is no hypoxemia. Okay. But to the question, is there hypoxia, looking at the AA gradient, here we need to work out first the alveolar content or alveolar partial pressure of oxygen, which if we work it out is 308. And now to work out the gradient, we're going to say the alveolar partial pressure of oxygen minus the arterial partial pressure of oxygen. So that will then be 308 minus 164, which gives us 144. Now a normal AA gradient is 15 to 20 millimeters mercury. Okay, so if we think about the fact that the normal arterial, a normal alveolar partial pressure of oxygen we worked out was 100 millimeters mercury, and a normal PO2, a normal arterial partial pressure is 80-85, you can see that the normal gradient should be about 15 to 20, right? So this is definitely a lot more. So yes, there is tissue hypoxia. Okay, now we're going to look at the reasons why the hypoxia is there. So there's basically three reasons why there would be hypoxia. And the first one is that there is a VQ mismatch. For example, if you have a pulmonary embolus. So you are ventilating, but there's no blood coming past. The next option is that you have a right to left shunt. So you are perfusing, but you are not ventilating. There's no oxygen being added into the blood. And then lastly, the other thing that you can have is a diffusion abnormality, where you are ventilating fine, you're perfusing fine, but there's something preventing the oxygen from getting into the blood. And these are basically the three reasons why there would be a hypoxia, why there would be an increased AA gradient. And that concludes the section on evaluating the PaO2. The second step in evaluating the ABG is looking at the pH. Now, I think we all know that a normal pH is between 7.35 and 7.45. And I think we all know that if it's low, then it's an acidosis, and if it's high, then it's an alkalosis. So you just literally need to look at the pH and write down whether there is an acidosis or an alkalosis, not interpreting anything, just stating what you see. The third step is evaluating the PaCO2. Right, now we know that the normal PaCO2 is between 35 and 45 millimeters mercury. Right. And we also know that if the PaCO2 is low, then we have a respiratory alkalosis. And if it's high, then we have a respiratory acidosis. So again, without interpreting anything else, you are literally just going to look at your PaCO2 and you're going to write down whether there is a respiratory alkalosis or acidosis. Does not matter what the pH is saying. We'll look at the compensation later. You are purely going to look at the PaCO2 and write this down. Just a little thing to remember, the pH will change by 0.1 for every 12 millimeters mercury change in the PaCO2, either up or down depending what the PaCO2 is doing. So that should help you just to work out how far you have shifted. But we will look at this in more detail when we come to the section on compensation. The fourth thing we are going to look at is the metabolic contribution to the pH. And there's a couple of things we're going to look at. First of all, the standard bicarb and the standard base excess. You must make sure to look on your blood gas that it says standard, because the calculated value means nothing. It must say standard. So the normal bicarb is 20 to 24. So let's take 24 as the absolute normal value. Now, what is your base excess? What is the mystery of the base excess? If we were to say that we take the bicarb scale and we reset it that 24 is now the 0 point, then any deviation from that 0 point is going to be your base excess. So basically, if your bicarb is 20, then the base excess is -4 or -4. If your bicarb is 28, the base excess is +4 or +4. Okay, so when they do say the base excess is the amount of base that you need to return the bicarb to normal, but basically what we're doing is we're saying that 24 is the 0 point on the bicarb scale, and any deviation from that is going to be your base excess. So I hope that makes sense to everyone. Okay, so the next bit is then just interpreting the standard bicarb and standard base excess. So if your bicarb is low and your base excess is negative, standard of course, then we have a metabolic acidosis. And if the bicarb is high and the base excess is positive, then we have a metabolic alkalosis, and that's what you'll be writing when you interpret your bicarb and your base excess. Again, make sure that it is the standard bicarb and base excess, especially if you're looking at a real-life sample. Well, now that we've determined whether there's a metabolic acidosis or alkalosis, there are 3 other things that we need to look at that also impact on our metabolic acid-base status. So these 3 things to consider. The first one, we'll write it as the concentration of ATOT. Basically what it refers to is the concentration of the non-volatile weak acids. And here we're basically looking at albumin and plasma proteins. These substances are actually weak acids. So it stands to reason, if these are acidic substances, if you have less of them, then you are going to be alkalotic because your overall acid amount is less. Conversely, if you have more albumin or plasma proteins, then you are going to be acidotic. All right, so I hope that makes sense. So we actually need to correct our pH according to the amount of plasma proteins and especially albumin that we have. The next thing we should look at is the strong ion difference. Now, what is a strong ion? A strong ion is any ion that will fully dissociate in solution. Sodium chloride, strong ions. Bicarb, not a strong ion. So we'll put the formula up here for you guys now that you can see. And important to note that things like lactate and urate are also strong acids. Now, when you have an increased strong ion difference, and that would be more than 45, the patient is actually alkalotic, right? And when you have a decreased strong ion difference, then the patient is going to be acidotic. Now, the reason for this is that when you have more strong ions in solution, they actually force the water molecule to dissociate. So we know water as just H2O, but under the influence of strong ions, they actually force the water molecules to go to H plus and OH minus, so it increases the amount of acid. Then the last thing that we should look at is the anion gap. Now the anion gap is not really useful. Your strong ion difference is actually more useful. We know the anion gap formula, but we can only really use this if you have a metabolic acidosis, and then it helps you to determine your differential diagnosis. So when it is increased, you can then look at some of the mnemonics for an increased anion gap metabolic acidosis, and if you Google cat mud piles, you'll find it. Normal level 8 to 16, so more than that, you're thinking about one of the cat mud piles conditions causing your metabolic acidosis, but it's not the most accurate thing to use. But if you will have to look at what information they give you. If they give you a lactate or a urate level, then you can work out a strong ion difference. If they don't, then you probably have to work out an anion gap. But it's just to help you to come to a final diagnosis. Well, now the last thing that remains to be done is to evaluate for compensation. So when you have a metabolic acidosis, you're going to compensate with a respiratory alkalosis. So let's work out your expected PaCO2 for the particular bicarb. And we do this with a formula called Winter's formula. And Winter's formula states that the expected CO2 is equal to 1.5 times the bicarb plus 8. And there's a range of plus or minus 2 on that. So if we now look at our blood gas example from earlier again, our bicarb on this is 20.9. So if we put that into Winter's formula, then we are going to get a CO2 of 39 with a range of 37 to 41. And our PCO2 here is 38.7. So that's exactly right. That's exactly what we would expect. So this patient isn't really acidotic, but just to show you how the formula works. Now, when we have a respiratory acidosis, we then need to look at what your expected bicarb is going to be. But now remember that you have both acute and chronic respiratory acidosis, and on a chronic level, you're going to have a bigger compensation. So when it's acute respiratory acidosis, the formula that we use to work out the expected bicarb looks like this. So it's 24 plus the actual PCO2 minus 40 divided by 10. So the bicarb will increase by 1 point for every 10 millimeters mercury change in the CO2. On the other hand, for chronic respiratory acidosis, because there's more time and the body compensates more, you'll see that the formula has a 4 in front of that little calculation we need to do in the brackets, because your bicarb will increase by 4 milliequivalents for every 10 millimeters mercury increase in the PCO2 above 40. Okay. And that's it, really. I really hope that these 5 steps will make you feel as happy as these little characters. But that's it, 5 simple steps. Have a look at some examples and just let me know if you have any questions. Bye.